Okay, ECT, we have talked about this. The only point that I want to stress, and probably I'll talk about that more in few minutes, is what you see here, that the absolute value, essentially the point is this: the absolute values of ECT are irrelevant, even though the values will differ based on where you look, where you monitor that, right? Why? Because doesn't matter how fast your fabric is or how fast your environment is, there's still the laws of physics. It's going to take so much time to transfer a frame from one location to another location, and then we take the time difference of the command and the response. It will differ the moment you move your reference plane, right? So we'll look into that in more detail, but essentially what is ECT? ECT is the total amount of time to take and to finish the transaction. And it is calculated separately for the read and the write traffic. And essentially, I would say this is the most important metrics, because this is what it's indicating the overall health of your storage, right? It all depends how fast. If it goes really low value, the lower values of ECT, that's good. If it's more, it's bad. And then you'll see that the rest of the things that directly impact ECT, if the DL increases, which is the next point, because DL is actually the subset of ECT, if the DL increases, obviously ECT will increase, right? There's no work around that. Or sometimes if we start seeing the frame drops, we see other things, we'll see that ECT instantly increases, right? So essentially, that's why you'll see that in DCNM SAN insights, at least today, our primary focus is on ECT. That's where we started from, saying that that's our primary use case, because everything has to do with how fast our exchanges are getting finished. Okay, so DL, the concept applies. I think the same bullet I'll highlight in a few minutes, that the values will differ based on where you measure these, but that difference is kind of irrelevant when we try to solve a problem, right? So technically, when we are just looking at these things from engineering point of view, yes, the values differ, but we want to solve a use case, right? All these deep dives are great to understand those minute details, but when we solve a use case using these metrics, this difference of the values is relevant. Okay, and this is what I was trying to say. So here is a simple example for you guys. Feel free to unmute and speak up. I've got two initiators here. I got one single target, and initiator one is accessing one LUN in target one, and initiator two is accessing another LUN within the same target. But the ECT of initiator one is 400 microsecond, and the ECT of initiator two, by the way, I got a spelling mistake there, is 800 microseconds. So while I fixed that spelling, any thoughts which initiator is performing better?
You would immediately think 400 is better than 800.
Yeah, see that?
But
maybe
right.
It's due to the size. Maybe it's due to the size of the exchange or the number of transfer IDs.
Yeah.
I'm sorry. But on this, maybe I'm a little confused. Wouldn't this mean that the blue LUN is transferring data back faster than the orange LUN, and
Maybe.
that the target has differences on maybe there's something going on with the target. Maybe if it's an array, it's the one LUN has a hotspot in it and the other one doesn't.
Mm-hmm. Yeah, all thoughts are valid, right? But the question is this: which server is performing better?
I don't think you can tell. I don't think
see that.
I disagree with being able to tell what server is performing better.
Yeah, that's exactly what I want to convey. Yeah. That just by looking at these numbers, you cannot tell, because there's so many other factors. To build on this example further, now I provide you more details that imagine now if you talk about the same both initiator one and initiator two, if the and let me fix that right away so that at least you guys know I know the spelling of initiator. If the ECT of server one or initiator one has been 400 microsecond, but it increases to 800 microseconds now. See in that graph? I think that's where I get concerned. I wouldn't really get concerned about the straight line value of 800 microseconds, right? Because it has been like that. Nobody has been complaining. The application is running okay forever. So that's okay, right? But if I get this additional detail, and let's say today morning, I see this kind of spike here and it stays like this is where I get concerned. Right. So now when somebody asks us that, hey, now which server is performing better? I mean, still, I can't answer that question, but I can always say that, hey, you know what? I want to investigate this initiator one, that what increased its ECT by 100%. So the other point that I want to convey that, guys, are you feeling the power of this baseline? Like you see that where that baseline thing comes in DCNM SAN insights, and then where this deviation coming, right? So here in this example, my baseline is what, like 400? So this is my baseline, and then the value spikes to 800, right? So how much of deviation that is? That's 100% deviation, right?
Right.
And this is not exactly the implementation of SAN insights. We'll probably never tell you guys that. Even I don't know, right? We need to look at the code, what exactly is happening there. But the overall concept needs to be clear, right? Like, what is the idea? So the baseline that we learn, because we never really know just by looking at the ECT values, we can never tell whether it's good or bad. And that's why we need to learn the profile of this application over a while, maybe over 7 days and 2 weeks. And then when it moves away from it, or especially increases, because remember, more the ECT, the worse it is. And not in absolute words, but in relative words. Yeah, and guys, these are the kind of conversations when we talk to those customers who say, I'm going to build something of my own. These are the questions they would be facing. The million flows thing, not even million, even let's just talk about 1,000 flows. I mean, 1,000 flows, alerting on those flows, making baselines, figuring out which is doing what. And those guys, like, they want to have a happy life, right?
Yeah,
they don't want to be doing this stuff.
If we had a view that would let us look at the, something maybe the deviation, the top so many flows that are deviating from the normal baseline by a significant amount, the top ones, that could help narrow down where to look further manually for the source of a problem.
Yeah, and by the way, we do that. If you remember those donut charts in DCNM SAN insights, that's kind of do, not exactly, kind of do what you're saying.
Okay.
Right, but essentially, as we progress towards, next level, you're seeing, right, what is the value of baseline, how do we calculate deviations, spikes and the learning over the period, 7 days or 2 weeks kind of stuff, right? This is the very basic concept behind that. And only when we are, and when we are only monitoring the ECT, this is one of the ways. I'm not saying this is the only way, but this is one of the ways which helps us to define or to find the answer of that problem. Is that server performing okay or not? Or is it getting worse or is it getting better? Okay, so when we know the ECT increases, the next question is, so when ECT increases, it's a very generic way of understanding, hey, you know what, my application may be slowing down, my server may be slowing down, right? Here in this example, like the application that's running on my initiator one may be slowing down. And because of 100 reasons, an application may slow down. One of the reasons is storage access. And by the way, that's a big reason, a lot of big reason, a big reason that application may slow down. So once we know that, we want to know why. Because storage, it's an ocean in itself, right? There's a SAN like storage, and we talked about all this complexity yesterday in the morning. So this is where DAL comes in play, because remember, what is DAL? DAL is essentially that initial delay within storage array. So if you see a graph like this, where your ECT moves from 400 to 800, and then your DL increases, let's say it was 300, and then it moves to 700. Yeah, maybe. Now, what it makes me feel is that my ECT increased because my DL increased, because this delay within the storage array increased. It went up, right? And that's why my ECT increased. So essentially, between these three components, is it a delay within the host stack, or is it a delay within the SAN? I would go and focus here on storage. because my DL increased in this scenario, right? So this is how we pinpoint further that the application may slow down due to storage access. And once we know that, we want to know where in the storage stack. So we go, in this example, we go and start looking within the storage array.
And just, I keep on interjecting here, but that would be consistent with congestion in the fabric causing TX wait at the storage port. So the storage array can't return data if we were doing reads, that is. I'm not sure if we're doing writes or reads now.
Yeah, but you know what? There are some exceptions to that too, because it's possible that the TX credits or the SAN congestion doesn't exist, but within the storage array, there's something specific to that LUN only. Those kind of things are possible. Let's say there are some other drops
on the actual storage array. It could be CPU bound and then not be accepting additional data. And there's lots of things on the array itself.
There's a long list, like, one thing that you mentioned, that's possible. The other things possible too. But at least, when we start pinpointing, so right now, right, like something storage. So you're going to look at the storage ports. You see that there are any TX waits, increases in TX waits, or any higher level of congestion. If you don't see that, you start looking within the storage arrays and looking at the logs there. Without this, we don't know where things are slowed down. Okay, so now we see the relationship between ECT and DL. By the way, this is an older way of showing it. It wasn't very clear, kind of, all over the place. So hopefully this explanation makes more sense. Okay, IO size, we already talked about this. Now there's a lot of use cases, minute use cases, the side use cases that what is IO size has to do with it, like the last two bullets. Probably not today. We'll talk about the use cases and how do you link these metrics to the use cases more in detail. We kind of covered like ECT and DL and linking them to use cases, application slowdown, server slowdown, things like that. I think it's important to understand, by the way, we'll cover more of that. Like when we say IO size, even though technically it's the transfer array length and block size, things like that, there's a difference the way we report it, right? So we'll go into that, like how exactly the SAN analytics repose these metrics, because right now we have been talking about very generic concepts that may or may not apply to SAN analytics. And IOPS, obviously we talked about that, the number of transactions initiated versus completed per second, right? Like that's a subjective question, but essentially IOs per second is IOPS. Throughput, it's a very generic concept. Different people think differently. Most people think it's megabytes per second or bytes per second, right? But again, open for interpretation. We calculate, or in theory, you can calculate bytes per or throughput by IOPS multiplying by IO size. In theory, practically it doesn't work like that. It's not as simple as that. Okay, we'll look into that. And outstanding IO, there are a lot of use cases. Probably, you guys can talk more about use cases, but some of the use cases that I'm aware of, obviously, is the queue depth value on the end devices. That's one use case that you'd like to get an estimation that what is my write queue depth, right? Like there's default values, but sometimes the default values are not good enough. That's one use case. The other use case is oftentimes these target ports have their maximum capacity of the open exchanges that they may have, right? They may have a limit on per port. They may have a limit of the overall storage array. So for some reason, if you are hitting that limit, let's say there are 2,000 open exchanges in a storage array and it cannot do more. So at least we know what the problem is. So those kind of issues we can solve using outstanding IO metric. All right, so the whole idea about that, where do we inspect the traffic and what metrics will differ and what kind of change it brings to us? Right, so I have a diagram here, and let's talk over this diagram, right? Because it's hard to put in crisp slides. So here's an example. The initiator initiates a read command. Let's say time T1. If you're looking at absolute time terms that flows, the read command will hit the switch 1, let's say at plus T2. right? There would be a couple of microseconds that it takes. And then it reaches switch 2 at T2 plus T3, and so on at target 4 at, at different points in time. Now, target takes a while. That's what DL, by the way, don't get lost in that DL thing. Don't get carried away that it's only a target delay. But in this case, if target is calculating the DAL, is actually going to report T5 as the value, because that's what it sees. And then it sends back data, and all, again, the data IU goes back to the initiator. And finally, there's like a time delta at every point. The moment a frame moves from one place to another, there has to be some time delay involved. That's the laws of physics. Right? The transactions gets completed, but that's not the point. Now, if you want to calculate, and if you're looking at a theoretical, let's say, science experiment in a lab environment with only one transactions with absolute awesome measuring devices that are probably packet traces at every location, you'll see that the target 5 or the target reports you the DL value of T5, right? The switch 2 reports a bit more. And the value reported by switch 1 would be even more. And the maximum value of the DL will be reported by initiator. Making sense? This value will differ. So let's say, just for the sake of example, getting a more realistic value, if the initiator says that my DL value is 420 microsecond, switch 1 may say it's 415, switch 2 may say it's 410, and if you're asking the target, it may say 405 microseconds. This is totally possible. In fact, this is how it works today. Okay, these are what we call as latency metrics, because essentially we don't calculate them from headers. We rely on the local clocks to take a time difference. And because the frames are going to hit these local clocks at different time, the time difference will exist. There's no doubt about that. However, there are some other metrics which do not differ. For example, IO size. Right? Because IO size, remember, it's sitting in the header. So it's the same header which is passed. It's getting started from the initiator, going to switch 1, going to switch 2, and going to the target. So if the read IO size is 4K, everywhere we are going to see 4K. Now, when we think about this whole concept in the baselining logic, and also what we're going to talk next about the way we calculate metrics in our NPU and send it to SAN Insights, you'll see that as more and more we progresses and takes these metrics to that whole journey, the absolute values go totally irrelevant in solving a problem. And probably, if not today, maybe when we talk tomorrow or on Tuesday, when we talk about NPU details, I'll probably have this like day in a life of a metric journey. And that's where you see that the way we calculate these metrics is not really we consume the metrics, because as I said in the beginning, this is a science experiment in a lab with an awesome measuring devices. In environment, it doesn't work like that, because you don't have one IO flowing ever. You have hundreds of thousands of millions of IOs out there. New IOs are being initiated as the previous ones are getting finished. And by the way, it's so hard to link that how many IOs an application will originate to do something. I don't know, right? So it's a totally multidimensional equation, and that's why these absolute values are less relevant. But it's important to understand the absolute values differ. There's no denying to that, but they are less relevant in solving a problem. They are great in an academic exercise, but not important for our customers. Okay, this is what I just explained. Okay, now let's get a bit specific to how exactly the switches collect the metrics, right? Those were generic concept, ECT, DL. By the way, the switch doesn't tell you ECT, right? So let's see how exactly the switch calculate ECT, or the SAN Insights gets to see it. Not very detailed in SAN Insights, but NPU level detail only for today. So we'll go into the more detail of the architecture of NPU, but essentially in NPU, there are different views. Views, nothing but like, think of a table, right, in a relational database. We maintain different views and we calculate metrics for them separately. If you remember very briefly, we talked about this yesterday, right? Depending on how you define a flow, we have views for that. So you can say an ITL flow, and we have views for ITL flows only. But then you can say, I don't care about those LAN level details, just show me the IOPS of a target port. So we have a view for target port that tells you all the metrics for target ports. Okay, but we'll go into details of it when we talk about NPU architecture, but just remember that there are different views based on what answer you want from the switch. Okay, when we try to classify the metrics, and by the way, when you execute the show commands on the switches, you'll see all these kind of crazy metrics. Overall, we can divide them into different categories. There are metadata metrics, which is data of the data, which is essentially tells you about your initiator, targets, LANs, and those numbers. Like you can ask, how many LANs do I have behind a target port? No, that's not IOPS, that's not throughput, that's not even ECT. That's just a metadata, right? Or I can say how many vSANs I have flowing on the wire. Now, that's a control plane construct, so you can do a show command and find that, right? But here we are also looking at the data plane, and the use case for that is, what is my traffic distribution per vSAN on an ISL port? That's something you cannot detect today without SAN analytics, right? It has been a long-standing ask, but with SAN analytics, you can tell that. Right, and that's a metadata thing, right? Like number of vSANs is a metadata, and then if you want to know the IOPS, that's what becomes a performance metric on it. Under performance metrics, we report via the NPU IOPS and throughput. They are reported at 4-second average. I'll cover more details of that. Why 4-second average? We also report a peak value, and then the numbers are accumulated over time. Then we have latency metrics where we report min, max, and accumulated values. We have error metrics, and then we have some time metrics. Okay, so let's look into these. This is very specific to the Cisco's implementation, right? These are not generic concepts, just to be clear. So these are the list of the metrics, right? I'll leave this as a reference. Let's go into detail of that. So essentially, these are the metadata metrics. As I said, the vSAN count seen on a port, the initiator count observed on a port based on the live traffic that's flowing towards the network side of it, right? That's really important. I have a drawing that conveys, and there's a quiz for you guys, right? For those of you who still have energy left. There's a target count metadata metric, IT flow count, TL or TN flow count, and ITL or ITN flow count seen on a switch port. And probably I should have some animation because, give me a second, I'll add some animation right here because I want to have a quiz for you guys, like right here. Okay, so let's start from here. Ignore those lines because I just did something crazy. This is your topology, 2 initiators, 2 targets. Both the targets have 4 LANs and everybody's talking to everybody. Initiator 1 is talking to target 1 and target 2, and initiator 2 is talking to target 1 and target 2, right? Ignore that wrong spelling of initiator. I guess I did a copy paste from one slide to another. So when you look at the host port that is connected to initiator 1, obviously one port can be part of, or one H port can only be part of one vSAN. Like I'm not talking about the F port trunking and all those scenarios, the usual scenario. So on this port, the number of vSAN count would be 1. Initiator count will also be 1. How many targets are connected to this port? 0. How many IT flow counts I have is number 2, because assuming this initiator 1 is talking to T1 and T2, how many TL flow counts I have? And I think I have a mistake here. It should be 4, but let's ignore that. ITL count is number 4, assuming this initiator is talking to 4 LANs, and rest of the 4 LANs, the other initiator is talking. Okay, so if you want to map the same number for this ISL port on the host edge switch, what would be the vSAN count? Assuming it's all in same vSAN. If you have two vSANs, yes, it can be 1 or 2, right? Let's say, there are two vSANs here, then we can have 2 number. If it's one vSAN, we're going to have 1. How many initiator counts? I think this is really important. How many initiator counts I'm going to have here? Anyone? Sorry for that. But the answer is 0 because remember, these values are detected from the network side. How many initiators can I reach via this port on the hosted switch is 0. However, I can reach 2 target ports on this ISL port, right? This is an important concept to understand. This is what you're going to see in your metrics, right? IT flow count. I think I'm going to see 4 IT flow counts here. Not, I think, this is for sure 4. And then ITL flow counts is 4 and 4. It should be 8, right? 1, 2, 3, 4. No, yes, 8 count.
Paresh, I'm not sure this is really clear because on this specific port, you said we can reach 2 targets. Well, yes, indirectly, because I have a switch in between this port and my 2 targets. So in the same way, I could say I can reach 2 initiators because I have a single switch in between my port and the 2 initiators. So I'm not really clear about what you're saying here.
Also, this is how it's implemented. Yes, you can do that, but it doesn't work like that. Okay, so when you execute a show command on the switch and you pull your metrics from this port, you're going to see your initiator count of 0 because you can reach 0 initiators from this port. Okay.
Okay, but
right?
I would
think
say
it like that. What do you reach from the network side of this port? That's what is going to give you an answer. Now, let me run parallels. Now, let's talk about, and I'm not going to bring that animated thing. I want to do it live. Let's look at this port. Okay. Now, what is the vSAN count here? Same, right? Because it's the same vSAN, 1 or 2, depending on how many vSANs you have.
It's 1 because they're all zoned together.
Yeah, see that? Yeah, that's right. I think because we are going to make that assumption, so let's just stick to 1 for the sake of clarity. Okay. How many initiator counts you have now?
In this theory, then it's 2.
Yeah, absolutely. That's right. How many targets you have?
None.
0.
None. Yeah. How many IT flow counts you have? Same, right? Now IT is like all over the place, right? I want T1, I want T2, I2 T1, and I2 T2. These are my 4 IT flow counts. And then how many ITL flow counts I have is the number of LANs, which is 8. Making sense? This is what you're going to see as your metadata metrics when you execute your show commands.
I can't say that it necessarily makes sense, but I can understand where you're going with it. This is how it's implemented. We can't really change it. This is
what the design is, right?
Why we're going to see what we're going to see, but does it really make sense? I don't know if it really makes like cognitive sense, but I follow where you're going.
Yeah, I mean, I'm not, this is not something a design phase. This is implementation is already done. I'm just trying to explain to you what you're going to see. So when you execute this command and you see this number, and then this number is 650. When you see this number 0, essentially I see 650 ITL flows and via a target, like the target is on the network side of this particular port, right? The IT, you see these two metrics are very similar, but one is 0, the other one is not. There's a reason for that because I don't see an initiator on the network side of FC133, and that's why this number is 0.
So this is either a storage port or an ISL?
Yes. It's an ISL port It's something, this can be a storage port. If we go back to our drawing here, this can be a storage port like this one, or it can be this one, because I have all the initiator values 0 here. I have target values here. Okay. I mean, this is an important concept, and I see that, you know, a lot of times people execute that show analytics command and say, hey, things are 0 for me. This is the reason things are 0 for you. Because it's a context sensitive thing. Your reference place is very important. And by the way, there are arguments like why it's implemented like this. I'm not going to go in detail. It's important. This is how it is. And when we see the output of the commands, it's important that we realize why it's the way it is and why the number is 0 and why the other number is not, right? This is the reason. That think about the network side, what you can reach from the network side, and that's what we show up there.
Yeah, what can I exit to?
Say that again?
What can I egress to from here?
Yeah. Towards the network side, or you can egress, you know, whatever helps you to understand it better, yeah. Okay, so this is the metadata metric. This is one category of metrics that we have. And by the way, we don't, you know, these vsend count is a generic term. We don't have a vsend count metric when you execute the show command. We have a logical port count metric, right? And you'll see that, like, similarly, initiator count, you see that the SCSI initiator count or NVMe initiator count is the real metric name. So there's a mapping for it, right? And you can see the table. And the details are available as part of that show command, show analytics schema. You should always, let's say 6 months from now, 6 years from now, whenever, always refer to the latest up-to-date, either documentation, but you know how great we are with documentation. So always look for the show commands. You guys know this better, but I'll do show analytics schema views, FC SCSI views. And I see some views here. We'll talk about this some point later, but you can do a view instance. And then let's say I pick a SCSI target view and I see the names here, right? So always refer to these names for exact the metric name. They may not directly correspond to our ECT metric, DL metric. Those are good for you know, user friendly names. Okay, so those were metadata metric. The next is error metrics. So we have aborts, failures, timeout, check conditions, reservation conflicts, queue fulls for SCSI. For NVMe, we go LB out of range, not ready, and capacity exceeded, right? There are some caveats with this. I'm not talking about that right now. We'll talk about that in one of the next sessions, especially the timeout metric. If you think about what happens when a command is received, but the response is not received, is it a real timeout or is it a what NPU sees as a timeout? Right, that's the key of the answer. But I'll cover more details later. But essentially, when you look at the output of the show commands, we see these metrics there. This is what the mapping is. Like aborts is not really aborts. We see read IO aborts. So check condition is not really check condition. There's a whole string for that. If it says read IO SCSI check condition count. Okay, and again, always refer to the output of show commands if you're doing something. Don't rely on any documentation, not even this slide. The slide will get dated eventually. You know, any documentation, as I said, you know how great we are with that.